Hello everyone. So in this video, I'm going to continue explaining some of the basic concepts that we learned in chapter 4 and expand on those ideas a little bit more. So the first lecture for this chapter ended on a discussion about how do we determine the position of an equilibrium in acid-base reactions. So briefly, I'm going to remind you what I discussed in that class once again. So acid-base reactions always favor the formation of the weaker acid and the weaker base. Acid-base reactions are under equilibrium control, and reactions under equilibrium control always will favor the formation of the most stable species. This is actually very important, okay? So in that class, I gave you two examples first. Remember, we talked about pKa's in the class. So the lower the pKa, the more acidic the compound is. For acids with pKa's below 0, so negative values of pKa's, these are very strong acids that are almost fully dissociated. The equilibrium thus is favored to the right. On the other hand, for acids with pKa larger than 0, positive values of pKa, those are weaker acids. The higher the pKa, the lower the acidity. And in that case, the equilibrium favors the reactants. An example of that is acetic acid, which is represented here in the slide. So by looking at the pKa values of these two acids in water, you can determine which side is the equilibrium favored. But what happens if you have a reaction in which, instead of water, you have an organic solvent? How do you determine the pKa? How do you determine, which side is the equilibrium favored? As I discussed in the class, if we analyze this acid-base reaction, we have here an acetic acid which is donating the proton, according to the Bronsted-Lowry theory, to ammonia to form the ammonium ion. Therefore, acetic acid is the acid, ammonia is the base, acetate is the conjugate base of acetic acid, and the ammonium ion is the conjugate acid of ammonia. So the acid on this side of the equation is acetic acid. The one acting as an acid on the right side of the equation is the ammonium ion. So a way to decide which way is the equilibrium favor is by looking at the pKa's of both acids. The pKa of acetic acid is 4.76. The pKa of the ammonium ion is 9.24. From these two, clearly, the strongest acid is acetic acid. It has the lowest value of pKa. If acetic acid is a stronger acid, then obviously it will donate the proton easier. Therefore, this reaction will be favored to the products. So wherever you have to compare or to decide which side is it is an equilibrium favor for an organic reaction, you basically have to compare the strength of the acids in the equation. The stronger acid will be the one donating the protons faster and therefore favoring the reaction. Here are examples that I discussed in the class, and I'm going to review again because I think they are quite important. So let's say we have an acid-base reaction in between an alkane, here is a hydrogen, and water. Water is the Lewis base because the oxygen has, remember, lone pairs. In this case, for a Lewis base, it's a species that can donate electrons to form a new covalent bond. That's the definition of a Lewis base. A Lewis acid with this hydrogen, and a Lewis acid is defined as a species that can accept electrons to form a new covalent bond. We use the curve arrows, as I also showed in that class, departing from the source of electrons and ending in the atom where the new bond will be formed. That's why we're showing here the new oxygen-hydrogen bond. And that will bring two species, obviously a positively charged hydrogen ion, oxygen positively charged, and a carbon ion, because these two electrons will be then going to the carbon. Now, if we have to decide which side is this equilibrium favor, we have to look in the reactants who is acting as a Lewis acid. In this case, the alkane pKa is about 51. And we have to look on the right side, which up to two species is acting as a Lewis acid. In this case, the hydrogen ion. pKa minus 1.8. From these two, clearly, hydrogen is way more acidic than the alkane, therefore, the reaction will be favoring the reactants. Here is a second sample. In this case, we have an alkene in water. The pKa of the alkene is again very high, approximately 50. The reaction shows the water acting as a Lewis base because of the lone pairs of the oxygen, forming a new covalent bond with a hydrogen and the electrons going over here. This will form a carbon ion and hydrogen. Once again, I have to compare the pKa of the acid in the reactants and the pKa of the acid in the product. Hydrogen is once again way more acidic. Therefore, this reaction will also be favored toward the reactants. And the same happens for an alkyne. If we try to deprotonate an alkyne with water, this will be the acid-base reaction, forming an acetaldehyde ion and once again hydrogen. We compare the pKa of the alkyne to the pKa of hydrogen, we see that hydrogen is way more acidic, therefore the reaction will be displaced to the left. So if we look at this data, we can conclude that we cannot use water ever to deprotonate an alkene or an alkyne. So that's a very important thing to keep in mind, okay? If we get to, as I said in the previous class, to deprotonate an alkyne, for example, we would need to use a base which conjugate acid is less acidic than the alkyne. That would be the idea. So whenever you want to use a base in an organic reaction, you need to use a base which conjugate acid is less acidic than the acid of the reaction. Here is another example. The reaction of an alkane with amide, NH2 minus. So this is a Lewis base. Once again, it's negatively charged. It can donate electrons to form a new covalent bond. Every hydrogen in the alkane is the same, so I'm using this one as an example. This will be the potential acidic hydrogen. New covalent bond over here, the electrons now will be going to the carbon, forming carbon ion plus ammonia. So the acid and the reactants is once again the alkane, and the acid in the product is ammonia, conjugate acid of the base. The pKa of ammonia is 38, pKa of the alkane is 51, so ammonia is more acidic. The reaction once again is displaced to the reactants. So we cannot use amide, sodium amide, for example, or any salt amides to protonate an alkane simply because the conjugate acid is ammonia, which is more acidic than the alkane itself. And the same applies if you try to deprotonate an alkene. In that case, once again, the conjugate acid of the base is more acidic than the alkene. Therefore, the reaction will also be displaced toward the reactant. So basically, none of this reaction will work. However, if we react an amide with an alkyne, the product of the amide will be once again ammonia and the acetylide. In this case, the pKa of ammonia is 38, the The pK of the alkyne is 25. Look how much more acidic is an alkyne as compared to an alkene and an alkane. We will see why in a little bit. In this case, the conjugate acid of the base is less acidic than the alkyne, therefore the reaction will be displaced to the right side. So indeed, because the alkynes are way more acidic than alkenes and alkanes, you can protonate an alkyne using a very strong base as an amide. Why is that? Because the conjugate acid of that base is less acidic as compared to the alkyne. This is very important, guys, because by analyzing pKa's of acids and conjugate acids, once again, you can make predictions whether or not some reactions in the lab will proceed successfully. So by predicting the position of an equilibrium, as I just explained, you will be able to predict the course of a chemical reaction in the laboratory. However, there might be cases in which you might not need to have the pKa's to make that decision. So how else can we determine the course of a reaction if we don't have pH values? And an answer to some of these cases by looking at the molecular structure. So let's see, what do I mean by that? So that's what I call the relationship in between acidity and molecular structure. Let's say we have two acids here, HA and HB, and we want to determine which of these two is a stronger acid. Let's assume we don't have the pKa values. So the reasoning that we are going to be doing, and this is important because once again, this class is about reasoning. So whenever I have to compare acidity based on molecular structure, I will be looking at stability of the conjugate bases. So HA will dissociate into A minus and hydrogen. A minus will be therefore the conjugate base of HA, and B minus will be the conjugate base of HB. So if I want to determine which of these two is more acidic, I will look at the stability of A minus and B minus. How will I know which of these two is more stable? Well, that will depend on the molecular structure of A minus and the molecular structure of B minus, and I will explain that in a few minutes. But for now, I want you guys to understand that if A minus is more stable than B minus, then HA will be more acidic than HB. The more stable the conjugate base, the more acidic the compound will be. So, the overriding principle when you determine the relative acidity of uncharged organic acids will be the stability of the conjugate base. The more stable the anion, the greater the acidity of the acid. So in the following slides, I will present 5 factors that will contribute to stabilities of conjugate bases. The first factor is electronegativity. One of the really important things when you compare molecular structure and you relate that to acidity, so you want to compare things that you can compare. I will give you an example of what I mean by that. Electronegativity is a factor that you will use when you compare a negative charge on two atoms that are within the same period of the periodic table. If you compare conjugate bases with charges on atoms that are in different periods, you cannot consider electronegativity because there will be other factors. But if you're comparing atoms that are within the same period, the greater the electronegativity, the stronger these electrons obviously will be held, and obviously the more stable the anion will be. So here is an example. Let's compare the acidity of three organic molecules: methanol, methylamine, and ethane. Remember I said in the previous class, when you look at an organic molecule, the first thing you have to decide is which is the most acidic proton. That is the one bonded to the highest electronegative atom usually. In this case, the one bonded to oxygen. This bond is highly polarized. There is a partial negative charge and a partial positive charge. This bond is weaker, is easier to be broken. That's why this proton is more acidic than the CH3. Remember, carbon and hydrogen have similar electronegativity. The same applies to the methylamines. The more acidic are the ones bonded to nitrogen. In the case of ethane, they are all equivalents. So we are basically comparing now methanol, methylamine, and ethane. If I want to determine which of these three is more acidic, what I need to look is at stability of their conjugate bases. First thing I need to know is to draw the conjugate base of each one of them. Here is the acid. The conjugate base will be losing the proton, the most acidic proton. That is the methoxide ion. This is the conjugate base of methanol. Here is the acid, methylamine. The conjugate base is minus a proton minus the most acidic proton, one of the ones bonded to nitrogen. Methylamide ion. Here it is. And for ethane, they're all equivalent, so that would be the ethylamine. So if I want to determine once again which of these three is the most acidic, I have to draw the conjugate bases and then determine which of these conjugate bases is more stable. So when I look at the conjugate bases, I see that the charge here is over an oxygen, here is over a nitrogen, here is over a carbon. The three atoms are on the same period of the periodic table. I see when I am comparing negatively charged species with the charge on atoms within the same period, the factor to determine stability is electronegativity. The most electronegative atom of the three of them is oxygen. Therefore, methoxide will be the most stable conjugate base. Therefore, methanol is the most acidic of the three of them. In order to see how important is electronegativity, you can see how carbon is in group 4, nitrogen is in group 5, oxygen is in group 6. Look at the difference in pKa's, 51, 38, and 16. It's a quite significant difference in acidity in between these three, just because of the different electronegativity in oxygen, nitrogen, and carbon. So remember, the negative charge is much better supported over a highly electronegative atom. The more stable is the anion, the stronger the acid will be. Okay? So if you have to compare acidity of organic molecules, you draw conjugate bases. This is the first thing you need to do well. Conjugate bases, you subtract the most acidic proton from the acid, and then you compare their molecular structure. Negative charge on atom from the same period, electronegativity is a factor. The most electronegative, that's the more acidic. Conjugate base is more stable. Remember, the fact that this conjugate base is more stable, it also makes it less basic. It reacts less than this one. Okay? So as a summary of this, electronegativity is a factor when you compare stability of conjugate base on an ions in which the negative charge is on atoms within the same period of the periodic table. What happens if you compare now atoms within the same group of the periodic table? And here is a very good example. Let's say we react methyl methaneethyl with methoxide. Clearly methoxide will be the Lewis base taking a proton here. This is the most acidic proton bonded to sulfur, and that will lead to a thiolate and methanol. And let's say we have to decide which side the equilibrium shifted towards to. So in that case, remember, I'm going to look at the acid on the reactants and the acid in the product. You have the pKa's here, but we don't even need to look into that. So if I need to determine which one is more acidic, methaneethyl or methanol, I need to look at their conjugate bases. Conjugate base is methoxide, negative charge on the oxygen. Conjugate here is the thiolate, negative charge on the sulfur. Oxygen and sulfur are in the group 6 of the periodic table. So sulfur is below oxygen. So if you go down on the periodic table, what happens with the size? It increases. Electronegativity also decreases. So the bigger the atom, the better it can accommodate this extra negative charge. So that's how size is a factor. So because atomic size increases from top to bottom within the column, stability also increases from top to bottom in a column. So if we compare these two, the thiolate, which is the conjugate base here, is more stable than the methoxide, which is the conjugate base here. Therefore, methanethyl is expected to be more acidic than methanol. And you can see the pKa values here, 10.4 versus 15.5, quite significant. If the methanethyl is more acidic, the reaction must be shifted toward the right side. So, as a summary of this, if you compare acidity based on molecular structure and the negative charge is on two atoms that are within the same column of the periodic table, the determining factor is the size of the atom that bears the negative charge. The larger the atom, the greater its stability, and obviously the greater the acidity of the organic compound. The third factor that can contribute to stabilizing conjugate bases is resonance. You know already at this point what is resonance. So we consider resonance theory when we have delocalized systems. 3 or more sp2 atoms next to one another properly aligned. The more delocalized is the charge, the more stable the anion will be. So when resonance is present, it's an stabilizing factor of the conjugate base, which actually makes the organic molecule more acidic. So let me give you an example here. Acetic acid reacting with water. So once again, water can behave as a base because of the long periods of the oxygen. In acetic acid, which is acting as an acid, the most acidic proton is the one bonding to the oxygen, which is the most electronegative atom in the molecule. The curved arrow is indicating a new covalent bond in between the oxygen and this hydrogen. That's the Lewis base forming a new covalent bond with the Lewis acid. Obviously, these two electrons now from this bond are going to go over the oxygen. That leads to the acetate ion. So acid here is acetic acid, conjugate base, base, conjugate acid. What about ethanol? Ethanol with water, same thing, in this case, water acting as a base, forming a new covalent bond with the acidic proton of ethanol that leads to ethoxide and hydrogen ion. So if I want to compare the acidity of acetic acid with the acidity of ethanol, I need to look at the structure of their respective conjugate bases. The conjugate base of acetic acid is acetate. The conjugate base of ethanol is ethoxide. So let's compare the acidity of these two based on molecular structure. As you can see, the negative charge here is over an oxygen, and the negative charge here is over an oxygen. It's the same atom. We cannot use electronegativity or size. Now, what is the difference in between these two? So this oxygen is next to an sp3 hybridized carbon, which basically means that this is not a delocalized system. The charge is fully localized over the oxygen. This negatively charged is next to a carbonyl, sp2 carbon, next to a double bond, which means that this charge is delocalized over here. Therefore, this delocalization brings stability to the acetate ion. So the conjugate base here is more stable at this conjugate base, because the only difference in between them is that this one is stabilized by resonance, whereas this one is not. Because this conjugate base is more stable, acetic acid is more acidic than ethanol. So when you compare stability of acidity of two organic molecules, you look at the conjugate bases. You must take into account resonance as a factor. Resonance is a factor that will stabilize the conjugate base and thus will make the organic molecule more acidic. Okay? This is just exactly what I said. Here are the resonance structures for acetate, which you should know at this point, everybody. So I won't really go a lot over this. So the fourth factor that can contribute to stability is something we call inductive effect. What is exactly inductive effect? So inductive effects are electronic effects that are transmitted through bonds. So basically what it means is when you have polarization of electron density in a covalent bond due to a significant difference in electronegativity in between those two atoms. Let me give you an example. So, and we will go back to this. Let's look here at these three molecules. 3-fluoroethanol. In 3-fluoroethanol, we have three fluorine atoms bonded to this carbon. Remember, fluorine is the highest electronegative atom in the periodic table. So these carbon-fluorine bonds are highly polarized toward the fluorine, making this carbon electron deficient. If this carbon is electron deficient, this bond in between these two are going to be also polarized toward the electron deficient carbon. And it's going to be transmitted over here too. So basically, by means of the presence of highly electronegative atoms over here, the conjugate base here will be more stabilized, because remember, you have a negative charge that is going to be stabilized toward this inductive effect. Same thing you can compare over here. Let's look at this carboxylic acid, butanoic acid, and 2-chlorobutanoic acid. If we need to determine which of these two is more acidic, let's look at the structure of the conjugate bases. The conjugate base here is obviously minus the proton of the carboxylic acid. Same thing here. So negative charge on the oxygen, negative charge on the oxygen. Both will be stabilized by resonance. In both, the negative charge will be on oxygen, so none of this is a factor. So what's the difference in between these two? Next to the delocalization here, I have a pretty electronegative atom. So the inductive effect of this electronegative atom that is attracting electrons toward itself, that will help to stabilize the charge, that will make this conjugate base more stable, and that will make this acid more acidic. Look at the significant difference in pKa's, 2.8 versus 4.8. So when every other factor does not apply, not electronegativity, not size, no resonance, if you do have an electronegative atom close to the negatively charged atom, that electronegative atom will help to stabilize the conjugate base. And because of that, the acid will be more acidic. The conjugate base, so you can also, and I want to mention this before I continue, the farther the electronegative atom is from the anion in the conjugate base, the effect will be felt obviously less. So here, look at the order of acidity. In this 3-fluoroethanol, the fluorine is in the carbon next to the one bonded to the oxygen, pK is 12. If you add a methylene group, so if it's farther away, the pK goes higher to 14.2 units, way less acidic. And if you add another methylene group, so even farther away, pK goes even higher, 15.4. So the closer the electronegative atom is to the negatively charged atom in the conjugate base, the stronger the inductive effect will be. So that's the fourth factor. And the fifth factor, which is something that we have already seen here, is hybridization. How can hybridization be a factor? So let's compare, for example, the acidity of an alkyne, an alkene, and an alkene. If we compare the acidity of an alkyne and an alkene and an alkane, first thing first, we're going to draw the structure of the conjugate bases. Conjugate basis of the alkyne minus a proton, acidic, is this, the acetylide ion. The conjugate base of the alkene minus a proton, all protons are equivalent here, will be this carbon ion, ethylene anion. And the ethyl anion will be the conjugate base for the thing, all protons equivalent. So in these three, if we want to determine, once again, we are comparing acidity of an alkyne, alkene, and an alkane. We throw the conjugate bases. Let's compare stability of conjugate bases. Here, the negative charge is on a carbon. Here is on a carbon. Here is on a carbon. Same atom. So at first, electronegativity does not apply at first. Size does not apply, same atom. No resonance. No inductive effect. There is nothing electronegative close to them. So what's the difference in between the three of them? The hybridization state of the carbon. In the alkyne, the carbon is sp hybridized. sp2 in the alkene, sp3 in the alkene. Remember, the effective electronegativity is different. 50% of S character in the alkyne, 33 in the alkene, 25 in the alkane. Higher the percentage of S, the most effective electronegativity is the carbon atom. So because of the hybridization, the effective electronegativity of the sp is much higher. That makes the conjugate base more stable and the alkyne more acidic. Look at the difference in pK: 25, 44, and 51. I have been saying in class many times that sp are effectively more electronegative than sp2 and sp3. Here, this is the experimental proof of that. And you can see by the significant difference in between 25, 44, and 51, how much more electronegative an sp carbon is as compared to an sp2 and an sp. Remember, a few minutes ago, I explained that an alkyne could be deprotonated with an amide, whereas the alkene and the alkane cannot. The only hydrocarbon that can be deprotonated is the alkyne, because that's the only conjugate base that is stable enough. has to be deprotonated. Why? Hybridization of the alkyne sp character 50% S character. Sp hybridization 50% S character. So when you need to compare acidity of organic molecules, if the negative charge is over an atom and the factor in between these atoms that you're comparing is only the electronegativity, the hybridization in each one of them, you will use effective electronegativity as a factor. So, in summary, the overriding principle in determining the relative acidity of uncharged organic acid is stability of the anion. So if you compare acidity of 2, 3, 4 molecules, you draw the conjugate base and you compare stability of conjugate bases. The more stable the conjugate base, the greater the acidity of the molecule. If you're going to determine stability based on molecular structure, there are 5 factors that you should be thinking about. First factor, when the negative charge is on atoms within the same period. In that case, electronegativity is the determining factor. The more electronegative the atom is, the more stable the conjugate base will be. Second case could be the negative charge on atoms that are within the same column. In that case, size is a factor. The negative charge, you want it to be on the larger atom. That will make the conjugate base more stable. Third factor, delocalization of the negative charge of the anion. That's when you have resonance. Fourth factor, inductive effect, when you have highly electronegative atoms close to the negatively charged atom of the conjugate base. The stronger the inductive effect, the more stable the conjugate base will be, and the acidic the compound will be. And the final factor is having the charge in an orbital with a higher percentage of S character, hybridization. So with that in mind, I'm going to stop this video. Everybody should be now familiar with the relationship in between molecular structure and acidity. And more importantly, you should be able to use that information in order to determine which side the equilibrium in a chemical reaction will be shifted towards to. Thank you.